Explicit notification. Explicit notification method, ELN method. A base station transceiver BTS detects the missing packets in the incoming TCP data stream from a mobile node MN. This is when the BTS gets a DACK DA from the MN. Explicit notification method, ELN method, works so that the BTS sets an ELN, explicit loss notification bit, when the DA is sent to the MN. When the MN gets the DA with the ELN bit, it retransmits packets. This is because the MN interprets the ELN bit from the BTS as signaling of packets loss. Alternative ELN2 method. Only the sequence numbers are buffered in the cache at the BTS in place of the packet. Whenever a DA corresponds to a buffered missing sequence number, the ELN bit is set with the DA. The MN retransmits on receipt of DA with the ELN. Another alternative. When the BTS receiver end is not able to transmit a packet to the MN, it sends an EBSN, explicit bad state notification, to the sender fixed line at the other end. The BTS can receive a packet from a sender at the other end, but may not be able to send it to the MN. Then, partial acknowledgement protocol provides for a notification. Sender retransmits on receiving notification. Indirect TCP. Indirect TCP suggests splitting of the TCP layer into two TCP sublayers. Figure shows indirect TCP sublayer between BTS and fixed node and conventional TCP between fixed nodes. TCP-M connection between the mobile node MN and the base transceiver BTS and between the BTS and a fixed node FN. The BTS has an access point at an agent TCP-M for TCP connection. Indirect TCP functions. TCP-M sends and receives the packets to and from the TCP-F layer at the fixed node. The transfer mechanism simple as there is only one hop. Retransmission delay between TCP-M and TCP-F is very small, unlike that between the fixed nodes. TCP-F layer at the fixed node sends and receives the packets to and from another fixed node TCP-F. TCP-F to TCP-F transfer mechanism is using multiple hops through the routers. Handover mechanism in case of indirect TCP. The data streams received from the service access point application at the MN and buffered at TCP-M. Figure above shows the handover mechanism. Handover mechanism when the MN visits a foreign network. Packets for transmission buffered at TCP-M are transferred to TCP-M. On handover, the socket, port and IP address and its present state migrate from TCP-M to TCP-M. The transfer from TCP-M to TCP-M has a latency period. Advantage of indirect TCP. Mobile part of the network isolated from the conventional. No change required in the existing TCP network. Disadvantages of indirect TCP. High latency period during handover of packets. Possible loss of data at the base. Deviation from the end-to-end connection feature of conventional TCP, which guarantees reliable packet delivery. Deviation. An acknowledgement to a sender may be lost during handover latency. Selective repeat protocol. Modification of the indirect TCP between TCP-M at the BTS and MN selective repetition of the data using UDP. Between TCP-M at one end and TCP-F and TCP-M at the other end, the data stream transferred as in the case of conventional fixed-end TCP. UDP, a connection-less protocol. Selective repeat protocol does not guarantee the in-order delivery between the BTS and the MN, unlike TCP. Figure shows modification in indirect TCP in selective repeat protocol using the UDP between BTS and MN. Mobile End Transport Protocol. Modification of indirect TCP guarantees the in-order delivery between the BTS and the MN like TCP. Data transferred between TCP-M at the BTS and the MN by using the Mobile End Transport Protocol. Data stream transferred between TCP-M at one end and TCP-F and TCP-M at the other end, as in case of conventional fixed-end TCP. Figure: modification in indirect TCP by using Mobile End Transport Protocol. TCP fixes snooping. Snooping TCP. Looking into or examining something secretly. A TCP connection splits into two, between the mobile node MN and base transceiver BTS, between the BTS and the fixed node FN. Some changes are made in the BTS and some at the MN. The BTS has a TCP-aware data link sublayer DLM. The sublayer DLM agent for snooping and buffering the TCP connection. Role of the agent DLM: ensures the delivery of packets to the MN in their incoming sequence from the fixed network. Attends to request from the MN for retransmission. Buffers during snooping packets from the fixed connection TCP-F layer for transmission to the MN on wireless. Also buffers the packets on wireless from MN for transmitting to TCP-F layer by a fixed line. Method for acknowledgements to and from the MN. Acknowledgements at agent detected on timeouts or duplicated acknowledgements detected from the MN. Acknowledgements at the MN detected by negative acknowledgement. A request for retransmission is conveyed to the MN in case the packets are not received or lost through the wireless network. Using snooping, the agent takes note of the acknowledgements from the MN and requests the MN for retransmission by sending a negative acknowledgement. Figure shows snooping at the TCP-aware data link sublayer DLM added at the BTS. Snooping TCP functions. Data streams are received from the service access point application at the MN and buffered at the agent. The data streams sent to the service access point application at the MN are buffered at the agent and then sent to the MN. DLM agent at the BTS also buffers the data and sends and receives the packets to and from the TCP-F layer at the fixed node. Transparent connection between the agent and TCP-F. DLM layer agent at the BTS sends and receives the packets to and from TCP-F and then from another fixed node TCP-F by multiple hops through the routers. DLM agent at the BTS snoops into the packet's data stream when sending and receiving to and from the MN. The agent and MN control the acknowledgements, lack of acknowledgements, and DACKs of the received data stream from the MN and to the agent respectively. Packet loss discovered at the agent from the timeout or DACKs from the MN. The DLM retransmits, if needed, to the MN in case of lost packets that are not acknowledged by the MN in the timeout period, or if there are DACKs. Packet lost discovered at the MN from the retransmission request from the agent to the MN. The MN retransmits to DLM in case of lost packets for which a negative acknowledgement is sent by DLM. The buffer empties to the fixed network through TCPF on receipt of an acknowledgement at the agent from the MN. The buffer empties to the MN on receipt of acknowledgement at the agent from the MN. The data stream transfer mechanism between the MN and DLM simple as in wireless networks. Only one hop in retransmission from DLM to MN. The delay is very small, unlike that between the fixed nodes. Snooping TCP. When there is handover of the MN while visiting a foreign network, the packets for transmission now snooped into at DLM at the other end. On handover, neither the socket port and IP address nor its present state migrates from DLM to DLM. Advantages of snooping TCP. Transparent end-to-end TCP connection without any transport layer changes. The mobile part of the network between the base and the mobile node has very limited isolation and is completely isolated from the base and a conventional fixed TCP connection. No change in the existing TCP network. Only a snooping sublayer is added at the base. Disadvantages of snooping TCP. Security risk involved in snooping. Difficulties in case of encrypted segment transmission. Insufficient isolation between the fixed node transport layer and the snooping layer in case of an asymmetric path, a fixed node connecting to the mobile node at the other end. The node at the other end does not have a snooping layer for retransmission and acknowledgement. Wireless TCP. A modification of snooping TCP. WCTP modifies the timestamp on the packets while returning acknowledgements to compensate for the increased RTT. Advantage of WTCP. Modifying timeout periods by enhancing timestamp time compensating for the increased RTT between the agent at the base and the mobile node. Useful when retransmission intervals are greater than the timeout period. Disadvantage of WTCP. Cannot be used on shared LANs. Delayed DACK protocol for delayed congestion response TCP/DCR. It is a modification of snooping TCP. Figure shows delayed duplicate acknowledgements protocol, a modification in snooping TCP. DLM agent is not TCP aware. The difference between TCP aware and unaware retransmission takes place in TCP aware DLM whenever there is timeout or DACK. Both of these indicates loss of packets. When a packet reaches the receiver out of order, TCP connection, for example, the TCP layer in the mobile node sends the DA. Further, the window is adjusted to a lower level for each instance of detection of packet loss, whether due to timeout or DA. Packet losses are due to two reasons: congestion and channel transmission errors. The channel errors are due to interference in the medium. Retransmission from the DLM takes place when there is timeout or acknowledgement from the MN, but the MN delays the DAC case so that the channel can recover from the channel errors. The MN attempts to reduce interference between data stream bits of the MN and retransmitted bits from DLM, delays the third and subsequent DAC case by a time interval TDA. When the first consecutive out-of-order packets COP reach, the MN responds by a DACK. When further consecutive out-of-order packets reach, each DACK is delayed by a period is equal to TDA. The MN no longer needs to send delayed DACKs. If the next packet is in sequence within TDA, the channel has recovered from channel errors. During TDA, the DLM MN channel recovers from channel errors. The MN may permit out-of-order packet delivery from the agent, and it may also look into the TCP header and reassemble the packets itself in order of sequence. Between DLM at one end and TCPF at the other, the data stream transfers as in case of conventional fixed-end TCP. Advantage of delayed ACK protocol. TCP headers can be encrypted as the agent is not TCP aware. Disadvantage of delayed ACK protocol. Duplicate ACKs are delayed. The retransmission of the packets lost due to congestion also delayed. TCP Reno. FRR phase sets in after 3 DACKs. TCP Reno protocol is a method of fast recovery by first halving the window size CNWD for fast retransmission, followed by fast recovery after each fast retransmission. When ACK is received before DACK and retransmission starts, it is called PAC. When PAC is received, in case lost octets are found by an ACK during fast recovery phase, then FR is stopped and wait constant window size phase sets in or slow starts sets in at region 4 after FRR1 and region 6 after FRR2. This method is used in fast retransmissions and fast recoveries in FRR1 and FRR2. Window is inflated for extending size after slashing by a factor of 2. Fast recovery ensures that TCP connection has a data stream to transmit. In FRR2, there is an extension of timeout period, region 4 for recovery in place of setting the window for a slow start immediately on receiving DACKs. Extension inflation of the window size refers to extending timeout RTT by inflating window in region 5 to recover the lost octets. There is an extended timeout in region 6 RTT after recovery. Advantage of TCP Reno. Increasing of the window size after fast retransmission sets large RTT. Recovers the lost octets. Lost octets may occur during handover of mobile node. Disadvantage of TCP Reno. Increase in RTT and window size may lead to congestion at the fixed part of TCP connection. TCP transaction-oriented. TTCP is used in situations where short messages need to be sent in sequence. Takes place after the SYN and SYN_ACK packet exchanges for connection establishment. Connection closes after the packet exchanges of FIN and FIN_ACK, closing, and last_ACK. Combines the three functions connection establishment, data transfer, and connection finish close for TCP data delivery. Only 2 or 3 packets are required for these functions. Figure shows transaction-oriented protocol function, TTCP functioning. There are no multi-way handshakes, for example, SYN, SYN_ACK, and established between the TTCPM and TTCPM ends. Connection messages SYN, SYN_ACK, established FIN and FIN_ACK sent along with the data stream and not separately. Sequence numbers for 2 paired bytes in TTCP instead of 1 as in the case of TCP. Only immediate like SYN and SYN_ACK in TCP and cumulative no piggyback acknowledgements sent. Acknowledgements are sent in TTCP. Piggyback acknowledgement. An acknowledgement sent by setting the acknowledgement field along with the data stream octets. TTCP employs caches for each state and RTTS at the transmitter and the receiver. Connection count CC used for keeping count of the number of bytes. The header has the sequence number of the first byte of octets in a data stream. TTCP server caches the CC for each connection at each end to restrict duplicate requests and replies. The data stream pushed during a preset timeout or sent as urgent by setting an urgent pointer. The timeout is set to a small value, for example 8 into RTT0, where RTT0 is time for one round trip with minimum window. TTCP thus becomes efficient for short data streams. Advantage of TTCP: increase in efficiency by reducing overhead of packets for connection establishment, data transfer, and connection close. Disadvantage of TTCP: mobile node TCP layer needs a change to enable the implementation of TTCP. Fast retransmit/fast recovery transmission. Slow start method presumes that congestion is the only reason for packet loss. In wireless networks, disconnection, handover, and channel errors due to interference causes congestion. When a mobile node MN moves from the home network to a foreign network, there is a lack of acknowledgement from the other end. The handover phase lack of acknowledgement is natural. CNWD can be set to CNWD divided by 2 and should recover fast to the value at which packet loss was detected. Method to recover CNDW back is called fast retransmit or fast recovery FRR. 4 phases of fast retransmit and fast recovery method. Beginning exponential. Fast retransmit/recovery phase 1 FRR1 on 3 duplicate acknowledgements. Fast retransmit/fast recovery phase 2 FRR2. Wait, constant timeout and window size. Figure shows 4 phases of fast retransmit and fast recovery method. First phase, beginning, exponential growth phase. Regions 1 and 2 in the figure above. The congestion window size for new data stream CNWD is equal to 1 at the beginning. After each RTT, after which the acknowledgement field is used to send the next data stream, the window is doubled till there are 3 DACKs within the set timeout interval. Example: let us assume that CNWD reaches a limit CNWD L0. CNWD is equal to CNWD into 2 for 1 less than or equal to CNWD less than or equal to CNWD L0, where CNWD L0 is the window at the limit 0 after which the FRR1 phase starts. The threshold is defined to control further exponential growth in order to avoid congestion. For example, let us assume that the exponential phase consists of up to the 11th round trip at which there are 3 DACKs detected within the timeout interval. Therefore, the limit 0 window CNWD/0 is equal to 210 and the number of segments transmitted is equal to 1 plus 2 plus 4 plus up to 512 plus 1024 is equal to 2047. FRR1 phase sets in after the 11th round trip. Second phase, FRR1, fast retransmit of fast recovery phase 1. Boundary of region 2 and 3. Forced by the MN on handover registration by sending a set of 3 DACKs. The window size for the new data stream CNWD by 1 is equal to CNWD by 0 divided by 2. Retransmission is fast because the link throughput is the same but the window size is now halved. Fast recovery region in FRR1. Region 3. In the subsequent streams, CNWD is equal to CNWD into 2 for CNWD L0 less than or equal to CNWD less than or equal to CNWDTH, where CNWDTH the limit of increments in window size for the recovery of lost packets. This happens when the data stream results in PACK, partial acknowledgement, and therefore to recover the lost packets, the window is inflated in this region. A set of 3 DACKs starts another fast retransmission. Example: assume that the exponential phase terminates at the 11th round trip. FRR1 phase starts at the 12th round trip. Now, if a lost packet is recovered in partial acknowledgement at the 13th round trip, then 3 duplicate acknowledgements are signaled in the 14th round trip as there are 3 DACKs in the 14th RTT period. Window size is 12th round trip is 2048 divided by 2 is equal to 1024 and in the 13th round trip it is 2048. Timeout set in the 12th trip is equal to 1024 RTT0. Timeout set in the 13th trip is equal to 2048. The number of segments transmitted from the beginning up to the 14th round trip is equal to 1 plus 2 plus 4 plus up to plus 256 plus 1024 plus 0 plus 1024 plus 2048 is equal to 5199. As the lost packet is recovered, the window size is no longer incremented and RTT remains at 2048 into RTT0, where RTT0 is the time when CNWD is equal to 1. Timeout set in the 14th trip is equal to 2048, and in that there are 3 DACKs, hence FRR1 ends at the 14th trip and FRR2 phase starts at the 15th trip. Third phase, FRR2, fast retransmit or fast recovery phase 2. The CNWD remains constant, region 4, equals CNWD by 1 is equal to CNWD by 0 divided by 2 before the beginning of FRR2. After this occurs the fast recovery, region 5. There can be repeated successions of regions 4 and 5 due to additional FRRs. 3 DACKs at any time in FRR2 will trigger another FRRJ, J is equal to 3 in case it is only one additional FRR, J is equal to 3 for first additional FRR, J is equal to 4 for the second additional FRR. Fourth phase wait / constant window size phase after the FRRs. Region 6. CNWD at the start of FRR2 in the 15th round trip is set to 2048 divided by 2. So CNWD is equal to 1024. In the 16th round trip, CNWD is equal to 1024 divided by 2 is equal to 512 for fast retransmission 2. In the 17th round trip, CNWD becomes 1024. In the 18th, CNWD becomes 2048 in the fast recovery phase. However, in the 18th round trip, there is a lost packet recovery as a result of retransmission after a pack. Hence, the constant window size 512 sets in and the wait phase sets in with CNWD is equal to 512. Window size for the new data stream CNWD is equal to CNWD by 1 divided by 2. It remains constant in order to recover lost packets. If there is a missing acknowledgement and consecutive DACKs, the slow start phase sets in. If there are 3 DACKs, again the FRRI phase sets in. Considering the case discussed in the previous example, CNWD at the start of the constant window size / wait phase in the 19th round trip is set to 512. CNWD wait is equal to CNWDL1 divided by 2, that is equal to 512. In the 20th to 24th trips, CNWD remains at 512. Any lost packet is recovered, and if a DACK is found in the 25th trip, then the slow start phase starts again on finding consecutive DACKs. If 3 DACKs received in antenna RTT, then FRRI starts once again. Advantage of fast retransmit or fast recovery method. Efficient in a mobile network when there are disconnections and handovers. Disadvantage of fast retransmit or fast recovery method. Wireless part TCP mixes with that of the fixed network and is not sufficiently isolated. The fast retransmitted packets can force congestion and not reach the destination over the fixed network part. TCP freeze. Timeout freezing of transmission TFT. TFT is used in situations where the mobile node MN faces long durations of disconnection. Figure shows TCP connections in timeout freezing of transmission protocol. Timeout freezing transmission functions. Agent DLTF senses a data link layer MAC the disconnection a little earlier than the TCP layer at the MN. The TCP layer stops sending packets when disconnection is sensed by the DLTF. The TCP layer presumes some congestion and therefore, after a timeout, the TCP layer freezes completely. During the timeout period, the MN may get some data sequences. After timeout, the TCP transmission freezes. The TCP, SYN and ACK data streams can still be received and transmitted through the lower layer with a suitable encoding by the header. When the DLTF agent senses the establishment of connection, it activates the TCP transmission. Figure shows TCP connection timeout freezing. Advantage of timeout freezing. Long interruptions of mobile node are accounted for and are independent of the data stream contents. Disadvantage of timeout freezing. Mobile node's data link layer needs to be modified by adding an agent to sense the loss and gain of connection and for making changes in the TCP layer at the mobile node to enable listening to the data link layer agent. Routing algorithms. Router. Terms and process involved in sending packets from a source to a destination. A router is at a node and receives packets from a neighboring node router source and forwards packets to another neighboring node router towards destination at a given instance. Each router maintains a routing table. Table must maintain an update in the rows, the destination and neighboring node addresses for that destination. Each router routing table catches the destination information regularly. Purpose of routing table is that it provides the presently available active paths for destination so that packet received from source is forwarded to another node in active path towards destination. Each router receives RREQ, route request packet, from a source so the source can discover forward paths for the destination. Router catches the RREP, route reply packet, from reverse paths from destination. Then it updates the route information in the table for each connected destination. Sends a RERR, route error packet, to the source when a previously active path to destination has developed link disconnection at an instance. Routing algorithm. Algorithm used for service discovery and for caching, maintaining and updating the routing table. Ad hoc networks are deployed for routing, target detection and service discovery. Routing protocol specifies the method used and faces sequences deployed for maintaining and updating the routing table at the nodes in the network. Following are some of the routing protocols. Dynamic Source Routing Protocol DSR, Ad hoc On-Demand Distance Vector Routing Protocol AODV, Temporarily Ordered Routing Algorithm TORA, Cluster Head Gateway Switch Routing CGSR, Dynamic Source Routing DSR Protocol, Deploys Source Routing. Each node caches the specified route to destination during source routing of a packet through that node. This enables a node to provide route specification when a packet source routes from that node. Each node deletes the specified route to destination during routing of error packet in reverse path to the source in case of observing a disconnection during forward path to destination. The deletion of link shown in a table or cache is called link reversal. Source routing means that each data packet includes the routing node addresses also. Reactive protocol reacts to the changes and dynamically maintains only the routing addresses from source to destination, which are the active paths to a destination at a given instant. Performs unicast routing. Unicast means routing packets to a single destined address. Phase in DSR protocol. There are two phases, phase 1 and phase 2 for source routing, caching of specific route addresses, reversal process of route address specifications. Phase 1 in DSR protocol. Source node initiates a route discovery process. It broadcasts the packets, each with a header. It then expects return of acknowledgement from each destination. The packets are called route request (RREQ) packets. DSR uses flooding, sends multiple RREQs. A header for each route request packet has the unique request number and source and destination addresses. This enables identification of request at each intermediate node in the request and acknowledgement packets. When the process starts, initially only the source address is given in the header. When the packet reaches a neighbor, that is, any intermediate node, the node adds its own address in the header if it is able to successfully send the packet to its next neighbor. When the packet reaches the destined address, its header therefore has all addresses of the nodes in the path. When packet reaches the destination, a route reply RREP for the sequence used in RREQ is generated. On return path, the route cache builds up at each intermediate node for deployment at a later instant of phase 2. Example: assume that node D is a source and G is a destination and the path D, E, F, G is not known. In such a case, the path cannot be placed in the header. Source header from D puts the sequence number Q and source address D in the packet header and sends the packet to its next neighbor. When the packet reaches E, its header is QD. Assume that no route error packet bounced back from neighbor E. The packet is then transmitted to F. When the packet reaches F, its header is QDE. Assume that no route error packet bounced back from neighbor F. The packet is transmitted from F to G. Assume that no route error packet bounced back from neighbor G. When the packet reaches G, its header is QDEF. Phase 2 in DSR. When any source node desires to send a message, it first looks at its route cache. If the required route is available in cache, the source node pulls all the addresses of the nodes for the path to destination in the header. Example: assuming that there is a message from a MANET node D in the network. Node D, destination A, cached path DCA. Node D, destination B, cached path DCAB. Node D, destination F, cached path DEF. Node D, destination G, cached path DEFG. The path specified at a source is dynamically modified when an alternative path to a destination has to be followed. The alternative path is cached when there is a root error packet generated in the reply. Ad hoc on-demand distance vector AODV routing protocol. A reactive protocol. Reacts to the changes and maintains only the active routes in the cache or tables for a pre-specified expiration time. Routes that are found are expected to be available at a given instant. Performs unicast routing. Distance vector means a set of distant nodes which defines the path to destination. For example, DEFG is a distance vector for source-destination pair D and G. In AODV, a distance vector is provided on demand during forwarding of a packet to destination by a node in the path and not by the root cache providing path through the header in the source data packet phase 2 in DSR. Every node keeps a next hop routing table which contains the destinations to which it currently has a route. A routing table entry expires if it has not been used or reactivated for a pre-specified expiration time. Ad hoc on-demand distance vector AODV routing protocol. AODV adopts the destination sequence number technique. Does not deploy flooding multiple RREQs. Stores the next hop routing information of the active routes in the routing caches tables at each node. Therefore, has small header size and thus reduces the network traffic overhead. Phase 1 in AODV protocol. A node uses hello messages to notify its existence to its neighbors. Therefore, the link status to the next hop in an active route is continuously monitored. When any node discovers a link disconnection, it broadcasts a root error RERR packet to its neighbor, who in turn propagate the RERR packet towards those nodes whose routes may be affected by the disconnected link. Then the affected source can be informed. Phase 2 in AODV protocol. Source node initiates a route discovery process if no route is available in the routing table. It broadcasts the demand through the RREQ packets. Each RREQ has an ID and the addresses of the source and destination in its header. It expects written acknowledgement from destination. A node identifies the last observed sequence number of the destination from the ID. Each RREQ starts with a small TTL, time to live, value, number of attempts. If the destination is not found during the TTL is increased in subsequent RREQ packets. The node also identifies sequence number of source node. Sequence numbers ensure loop-free and up-to-date routes. Loop-free means free from bouncing of a packet to a node after intermediate hops. Each node rejects the RREQ which it had observed before. This reduces flooding, which means it reduces too many RREQs present in the network at a given instant. Route table in AODV keeps entries for a specified period and each node maintains a cache. The cache saves the received RREQs. Only the RREQ of highest sequence numbers are accepted and previous ones are discarded. The cache also saves the written path for each RREQ source. When a node having a route to the destination or the destined node receives the RREQ, it checks the destination sequence number it currently knows and the one specified in the RREQ. RREP packet is created and forwarded back to the source only if the destination sequence number is equal to or greater than the one specified in RREQ. It guarantees the updating of routing cache information. Uses only symmetric lines and RREP follows the reverse path of respective RREQ. Each intermediate link on receiving the RREP packet updates the table discarding the previous entry and forwards back the RREP to its neighbor in path to the source. Temporarily ordering routing algorithm TORA. A reactive protocol. Reacts to the changes and link reversals. Employed for highly dynamic MANETs and provides an improved partial link reversal process. Discovers the network portions showing the link reversals. Has a feature that it stops the non-productive link reversals in a given portion of the network. Assumes addresses of the routers in the path and of source and destination for one set of input route. Each node provides only one set of subsequent route addresses. Network shows a directed acrylic graph topology, means one input path and one outgoing path. Possesses network capacity such that many nodes can send packets to a given destination. Guarantees loop-free routes, no bouncing of a packet to the node once it transmits to intermediate hops. Supports multicasting from one source to multiple destinations. Unlike AODV, but similar to DSR, TORA supports unidirectional links and also provides multiple routing paths. It does not exchange hello messages periodically to listen to disconnected links as done by AODV. Phase 1, 2 and 3 in TORA are route creation, route maintenance and productive useful link reversals, vector discarding. Cluster Head Gateway Switching Routing (CGSR). A hierarchical routing protocol. Proactive protocol. When a source routes the packets to destination, the routing tables are already available at the nodes. A cluster higher in hierarchy sends the packets to the cluster lower in hierarchy. Each cluster can have several daughters and forms a tree-like structure in CGSR. Forms a cluster structure. The nodes aggregate into clusters using an appropriate algorithm. The different clusters can be assigned to different band of frequencies in FDMA or different spreading CDMA codes. CGSR algorithm defines a cluster head, the node used for connection to other clusters. Also defines a gateway node which provides switching, communication between two or more cluster heads. Three types of nodes in CGSR. Internal nodes in a cluster which transmit and receive the messages and packets through a cluster head. Cluster head in each cluster such that there is a cluster head which dynamically schedules the route paths. It controls a group of ad hoc hosts, monitors broadcasting within the cluster and forwards the messages to another cluster head. Gateway node to carry out transmission and reception of messages and packets between cluster heads of two clusters. Cluster structure. A higher performance of the routing protocol as compared to other protocols because it provides gateway switch type traffic redirections and clusters provide an effective membership of nodes for connectivity. CGSR. Phase 1, 2 and 3 of CGSR are routing path discovery and caching, maintaining update and distribution respectively. The basic processes of CGSR are cluster definitions and selection of clusters for routing. Algorithms are used for both the processes. Phase 1. Routing path discovery and caching. Each node maintains a routing table that determines the next hop to reach other clusters. An algorithm that can be used in this phase is the Destination Sequenced Distance Vector (DSDV) algorithm. It means it finds the next hop to the distance destinations. Cluster member table is created using sequence numbers in RREQ packets which are broadcast periodically. Phase 2. Maintaining routing information. A clustering algorithm used for maintenance of routing information is least cluster change (LCC). Cluster head changes only when one of the nodes moves out of range of all cluster heads in the cluster or two cluster heads come within one cluster. A token-based algorithm can be used to control the transmission within a cluster. Cluster head should get more chance to transmit as it is in charge of broadcasting within the cluster and of forwarding packets between nodes. Cluster heads are given priority such that route path utilization is maximized and packets are transmitted with minimum delay. Another algorithm is the priority token scheduling (PTS), which gives higher priority to neighboring nodes from which a packet was received recently. Each node dynamically maintains a cluster member table. Algorithm is such that node will periodically change entries in its cluster member table when a new sequence number entry is received from neighbor after successful RREP. Table rows map each node to its own cluster head. Node transmits its cluster member table periodically. After receiving broadcasts from other nodes, node uses a DSDV algorithm to update its own cluster member table. Mobile Internet Protocol. Introduction. The Internet Network Layer Protocol (IP) is the widely used network protocol today. Mobile IP network layer facilitates internet-based communication between mobile nodes (MNs). IP and mobile IP network layers. OSI, Open Systems Interconnection, defines 7 layers for data communication. TCP/IP is the most widely used models having 5 layers. Network layer, layer 3, uses IP in this model. OSI Open Systems Interconnection 7-layer model. The figure below shows the 7 layers of OSI. OSI Open Systems Interconnection 7-layer model. Physical layer L1 for sending and receiving signals wirelessly. Example, TDMA or CDMA coding with FEC or over wire or fiber. Data link L2 for linking to the destination computer by MAC address. Network L3 for routing through a chain of routers. Transport L4 for defining, sequencing and for repeat transmission. Session L5 for defining the transaction and session protocol for establishing end-to-end connectivity. Presentation L6 for defining the data encoding format. Application L7 for running a web browser, mail transfer or mobile e-business application. L7 to L1 data transmission. A physical network transmits data of one end application L7 to another end application L7 through the various intermediate layers. At a layer, data received from the upper layer can be suitably divided, for example, packetized at the L3 IP layer. At each layer, data or each section of data suitably encoded, for example, by adding a header for transmission to the lower layer. L1 to L7 reception. At the receiving end of the network, the bits in the header fields are decoded, for example, by extracting the header upon reception before passing the data to the upper layer. L2 and L1 layers, usually associated with the communication and physical network radio and switching infrastructure, for example, in GSM or CDMA systems. L3 layer, for networking, using a path chosen among the large number of paths available through a chain of in-between routers. IP protocol, mobile IP protocol. L4 layer, data transfer after a session is established through the session layer L5 between two ports on the networks to the L4. The protocol header fields of this layer define the sequences and other required fields for data transfer to and from a port in a network. L5 layer defines how various sessions are established, for example, a call setup session. Not present in the TCP/IP model does not provide for a separate session layer and establishment and close functions included at L4. L6 layer defines how the data from the port is to be presented or formatted. Not present in the TCP/IP model does not provide for a separate session layer and presentation functions included at L7. L7 layer supports multiple applications. Defines a protocol for transferring application contents and data of a port. Each port application defines a service access point at the L7 layer. Each port deploys a protocol for data transfer between the L7s at the transmitter and the receiver. An output port transmits the service application contents and data employing a distinct protocol. Example: HTTP, Hypertext Transfer Protocol. A corresponding data input port software at the receiver L7 layer, service access point. Same protocol used to retrieve the service application contents and data as during transmission. Example: HTTP, Hypertext Transfer Protocol. A port number can be defined for each application. A port can be numbered in order to define and distinguish each application's data easily. Example: HTTP port in the TCP/IP model, through which all the HTML files are transferred through the network, is numbered 80. The below figure shows OSI layers quick summary. Internet Protocol IP. The basic protocol at L3, which is used for transmission over the Internet. Designed for use by networks which employ packet-switched data communication. Provisions the transmission of data packets. Each packet treated independently. Every packet must contain complete destination addressing information. Packet formation in IP. Packets of maximum size is equal to 216 bytes 214 words after the data from L4 transport layer divided. A packet-switched network can be used for transmission. Hopping of data packets use different routes to reach a destination. More packets can be sent simultaneously through the network, unlike in a circuit-switched network where only one data frame can be transmitted at an instant, for example, in GSM or HSCSD. Header, source and destination IP addressing. IP specifies certain header fields. A field is a set of bits placed in a word for a specification, condition, or purpose. Encoding data from the transport layer at the transmitter. Decoding the data received from the data link layer before passing it to the transport layer at the receiver. Header fields are as follows. First word. 32-bit word to specify IP version, IPv4 or IPv6 for Internet or broadband Internet. Length of the IP header. Precedence of the IP packet. Total packet length including L3 layer for encoding. Second word. 32-bit word. ID for the packet. Flags. Fragment offset for the fragments of same ID. Third word. 32-bit word. Time to live, not in seconds but in number of attempts to hop before expiry of packets in the network. Type of protocol. Checksum of the header for finding transmission errors if any. Fourth word. 32-bit word. IP address of the source as per 4 decimal numbers, each separated by dots and each lesser than 256. Example. Source IP address for routing is ns1.ns2.ns3.ns4. Fifth word. 32-bit word. IP address of the destination. 4 decimal numbers, each separated by dots and each lesser than 256. Example. Destination IP address nd1.nd2.nd3.nd4. Packet transmission from the source IP address to the destination. By hopping among the various routers on a path. Paths can be different for different packets from the same source. Path for the routing of a packet depends on the paths and subpaths which are available in the network at a given instant. Point-to-point, multicast and broadcast. Point-to-point or unicast transfer. Message or packet transmits to the destined IP address only. Multicast transfer. Message or packet transmits to a group of IP addresses. The IP protocol specifies the use of a Class D subnet for multicasting. Multicasting subnet has 4 MSBs 1110 in the net ID part of the IP address for defining subnet as multicast network. 32 minus 4 is equal to 28 bits specify the address for the multicasting net ID and the subnet and host S and R addresses. The address 224.0.0.1 multicast to all hosts in the links of a router. NS1 is equal to 224 in decimal system is equal to 111,000,000 in binary system. Multicasting can be used for flooding a UDP, user datagram protocol on the network. Flooding is required for advertisement. It means sending information along many paths. Spanning tree protocol, protocol to block nodes which have already received the relevant information during flooding. Conclusion. In this chapter, we have covered the following in detail. Limitations of TCP in mobile wireless systems. TCP fixes snooping. Indirect TCP. TCP variants, fast retransmit or recovery. TCP Reno. TCP freeze. TCP transaction oriented. Explicit notification.